Okay, so welcome to college algebra. Last time we were talking about the distance formula, so now let's get that down. So the distance on the line. So the distance on the line conceptually is that we can select 2 points, and if we name them, if they have values A and B, then the conceptual model is that we get out our agreed upon ruler, our linear measurement device, and we read out what the ruler reads. Okay, but we want a formula for this, for the distance. So what is the formula for the distance from A to B? What's the formula? So what will it be? I heard A minus B. Okay, so how about that? Do we like that, A minus B? So I hear some objections. So what's your objection?
It's wrong.
Okay. Can you be more specific?
It's B minus A.
It should be B minus A. That is, unless I draw another picture when B and A are in the other order. And then this one is right, and you'd be wrong, right? So by the way, how do we know that the expression should be B minus A and not A minus B? B's the bigger one? How can you tell that B's the bigger one?
It's more right to the right.
It's further to the right. Okay. So then how do we make this correct so that no matter if I draw another picture with B and A in the other order, that we always get it right? Huh? So let's be specific. So let's suppose that one of the numbers is 13 and the other 20. What is the distance between these? 7. What is it? Okay, there we go. This is how we always select the correct version. Because in that specific example that I gave, right, 20 minus 13, that's 7. Whereas 13 minus 20, that's negative 7. How do we always select the non-negative one? With absolute value. Okay. So on the plane, now the picture looks like this. We have 2 points still. We have point A, and we have point B. And what we want is we want the distance between them. That is to say, we want the length of this green line segment. So that we want that length. However, so what we do have, the tools at our disposal, is that we have a ruler that can be used on this line, and we have a ruler that can be used on this line, the vertical one. But it is absolutely forbidden and not permissible for you to take this ruler and just measure the distance between A and B directly. So how do we go about it? I didn't make up the rules, okay, but these are the rules. So how do we go about finding the distance between A and B? Okay, good. So using that same procedure, we could find the coordinates of A and the coordinates of B, right? So then we could drop point A down to this line, and we could drop point A over to this line. And let's say that in doing that, we determine that this is point x1 on horizontally, and that this is point y1 vertically. Okay, then we can do the same thing for point B, because if it worked for A, it'll work for B. And let's say that for B, we determine on horizontally that this is x2, and vertically this is y2. So if you like, you could say that this is point x2, y2, and this point here is x1, y1. Okay. So this shape right here that's a triangle, and in particular it's a right triangle. And the green line segment is what with respect to that triangle? It's the what? The hypotenuse. The hypotenuse. So how about this distance right here? Can we measure this length? So what is it? So what is it?
X2 minus y, x1.
No? That's almost right,
Yeah.
but it's not right.
The absolute value.
Thank you. The reason why it's not right is because I could give you a different diagram where the points are arrayed in different orders. So you need absolute value. So how about this one?
Absolute value, y2 minus y1.
Very good. By the way, would it matter? So you started to say y1, absolute value of y1 minus y2. Would it have mattered if you had continued? It would not have mattered. Okay. So then we have, what we want is that green line segment, which is the hypotenuse of a right triangle. And what we have are its legs. Right? When you have a right triangle, the sides that are not the hypotenuse are called the legs. So if only there was some kind of theorem that related the length of the hypotenuse of a right triangle to the length of its legs. Ah, the Pythagorean one. Good. So then, if we refer to this as the distance from A to B, that length, then the Pythagorean theorem tells us that the distance from A to B squared should be the one leg squared plus the other leg squared. Okay, so that's directly quoting the Pythagorean theorem and substituting in the relevant bits. So now I'm going to do something, and I want you to tell me two things: what I have done, and also if it is legitimate to have done it. So what have I done? I got rid of the absolute values, which is interesting, because I made a big show about them being so important over the last 5 minutes. But now I don't have them. Is it legitimate to not have them? Well, let's think about it for a minute.
It depends on the numbers, right?
Well, let's think. So if x2 minus x1 is, say, -5, then to evaluate this term that I'm pointing at, that would be -5 absolute value, which is what? 5, and then we square it, which is what? 25. So supposing that we don't do this intermediate flipping the sign of the -5.
It's okay because it's a square, it's still positive.
It'll still work out because we're squaring. Okay? It'll still work out. So yes, in fact, you can do this without absolute values. So then now if we compute square root of both sides, so the distance from A to B is the square root of x2 minus x1 squared plus y2 minus y1 squared. And so here's a formula now that you're expected to memorize. Okay, any question about the statement of the formula before we do one? Okay, so let's do one. So for example, find the distance from -3, 8 to, how about 10, -7? Okay, well, in the interest of time, I hope that we can all agree that the shape of the formula is this. It is something, the square root of something squared plus something else squared. So that's the shape of the formula. In the end, it must look like this. And now it's sort of a question of correctly routing the various bits and pieces into the right place. So what goes in here?
X2 minus X.
Right. So I need to take, this is the difference of the x's in this one. So this one can go here. And then what one goes here? The 8? Right, the 10, right? Because this is the difference in the x's.
Maybe 10 minus -3, or does that not matter?
It does not matter. So the question is do you need to do this one minus that one or that one minus that one? So the distance from here to Houston is on the order of 200 miles. How about from Houston to here? It's got to be the same, right? So your question, does it matter which order you do it in? The answer is that it cannot matter, for the same reason that the distance from Dallas to Houston must be the same as the distance from Houston to Dallas.
Squaring it, you'll get the same answer.
Right.
Okay.
That's the arithmetic reason. Okay, so then what goes in? What goes here? Right, the 8, 7. Okay, so then I'll write these bits in now. So -3 and then -10. Okay, and then 8 goes here and then -7. I'm waiting for it.
Isn't there a negative sign?
Thank you.
So
Right.
it'd be plus.
So it'd be 8 plus 7.
It would be 8 plus 7. Right? But this represents one of the most common arithmetic errors that I observe students make. So it's 8 minus -7. No, you don't need to write minus -7. You can just write plus 7. But I want you to see what's happening here. Okay, so then this will be the square root of, well, -3 minus 10. That'd be -13 squared. And then plus 8 plus 7, that'd be 15. Square that. So that'd be square root of 169 plus 225, which is 380.94. Beautiful. Okay. So any question about this one? Yes?
So we shouldn't square root. We just leave it like that.
Well, you should do whatever the instructions say.
Oh.
So if the instructions don't say to do something, then please don't. Okay, but I think the homework says something like express it in simplest radical form or whatever. Yeah, that means start factoring things out as possible. Okay, so another matter we need to deal with is just like distance, quite similar to distance, is this one. So proposition, midpoint. So on the line, by midpoint, what's meant is that you take 2 points and we want the point that's right in the middle. So we want that point. Okay. Well, what if I asked you about what's the midpoint of 10 and 20? 15. Most people can respond to that one quite readily. Okay, what's the midpoint of negative 3 and 17? Oh, it's a little bit not as good, right? It's 7. Yeah. Okay. Okay, so then now, the first question that I asked, what's the midpoint of 10 and 15? When I ask students to tell me how they do it, they more or less do this. They say, well, the distance between those is 10, and half of 10 is 5, and so if I add 5 to 10, then I get 15. More or less, students do something like this. And that just breaks down entirely when students are faced with arithmetic. But you could do it the exact same way. You could say, well, the distance from negative 3 to 17 is 17 minus negative 3, which is 20. Half of that is 10, and so if I add 10 to negative 3, that's 7. But the arithmetic is a little more bothersome. There's actually a much simpler way to do this. Is you just add up the numbers and divide by 2. Right? The midpoint of 10 and 20 is, well, what's the sum of 10 and 20? 30, and what's half of that? 15. The midpoint of negative 3 and 17 is, well, what's the sum? 14, and half of that is 7. Okay. So the formula is a plus b over 2. Any question about the midpoint for the line? Now we want the same thing for the plane. So again, we have the same story, similar story, is that here's point A and here's point B. And conceptually, there is a line segment that's joining them. And what we want is the point that is on this line segment that is exactly halfway between them. So we want this point. Okay, but it's forbidden for you to get out your ruler and do any of that. Okay. So, how are we going to do it? How are we going to do it? Well, how do we take care of the distance problem? The Pythagorean theorem. But even before we got to the Pythagorean theorem, we had to resort back to these two axes where we can actually perform measurements. It's not the Pythagorean theorem divided by 2. Okay, well, same story as before. Let's take this point. Let's take these points and figure out their coordinates on each axis. So supposing that this is horizontally x1, and this one is horizontally x2, and this one is vertically, this one is y1, and this one y2. Okay, well, now that have two axes that we can deal with, well, we could find the midpoint of this one, right? The midpoint of this one is right here, right? What's the formula for that midpoint right there?
X1 plus x2 divided by 2.
So we know that. We did it on the horizontal axis. But if we did it on the horizontal axis, where else could we do it? We could do it on the vertical axis. So the midpoint of these is about right here. And what's the coordinates of this vertical midpoint? Very good. And so now that I have all the relevant bits drawn, who can tell me the punchline? What do you think? So this is the point that we want. How many numbers, because this is a point on the plane, how many numbers does it take to describe it? 2, right? A first coordinate and a second. Well, look. The first coordinate got to be that, doesn't it? And the second coordinate? It's got to be that one. So what are the coordinates of that point? x1 plus x2 over 2 in the first coordinate, comma, y1 plus y2 over 2. So, if you have 2 points, the midpoint of those, well, the x-coordinate is the average of the x's. The y-coordinate is the average of the y's. And if we were in 3-dimensional space, and we were calling points x, y, and z, then the x-coordinate would be the average of the x's, the y-coordinate the average of the y's, the z-coordinate the average of the z's. And if we had 1,000,000 coordinates, if we were in a 1,000,000-dimensional coordinate system, then you'd have to average all the individual coordinates. Beautiful. So any question about this one? Okay, so any question before we move to something completely different? So we're okay with this? Okay. So now, we're in section 2.2. Which is called equations in one variable. Okay, so let's have an example. So here's an example of an equation in one variable. 3x plus 8 is equal to x minus 9. So this is an equation in one variable. So this bit right here, notice that there's an expression here and a different expression there. So it's 2 expressions, and they're separated by this thing in the middle. So this is called the equal sign. Okay, everybody knows that. The name for this expression, this is called the left-hand side. And what adventurous student wants to tell me what this one is called? The right-hand side. Oh, yeah. So probably no surprises here. So this is said to be an equation in one variable. Why? Because it only has one variable. Okay. So mathematicians are a notorious group of people who name things like this. Okay, now here's where things will, for most of you, not all of you, but for most of you, is going to get weird. Okay, now my first request of you is please evaluate at x is 2. So what is it that I'm requesting of you? Yeah, I want you to replace all instances of x with 2, and then tell me about that. Okay, so that's a good response, or that's a response anyway. So what I am requesting of you is that I want you to take this equation that I gave you, 3x plus 8 equal x minus 9, and I want you to plug in 2. So 3, and then here comes a 2, and then plus 8 is equal to, here's another 2, 2 minus 9. So if we were to do this arithmetic, that'd be 3 times 2 is 6 plus 8 is 14. And then the right-hand side would be negative 7. Okay, so I'd like to make a comment. First comment is that some of you are probably feeling just a little bit uncomfortable that I've written this on the page. Feeling a little emotionally uncomfortable. That's because you've been systematically conditioned to have an emotional response to these things. So now here's a question. Is this an equation?
It has an equal sign.
It is an equation. It has a left-hand side expression. It has a right-hand side expression. And in between them is an equal sign. Is this an equation? So we've got to say it out loud. Be comfortable with it. Is it an equation? Yes. Now here's what you're uncomfortable with, is that your former instructor wasn't clear about the type of things versus what they evaluate to. Now here's the question that you were expecting. This equation, does it evaluate to true or does it evaluate to false? False. Okay. So is it an equation? Yes. What is its evaluation? False. There's nothing immoral or unethical about this statement. It's an equation. It's false. No problem. Okay. Now here's a separate request. Please evaluate at negative 17 over 2. Okay. So in the end, what I'm requesting of you is I want you to take 3x plus 8 equal x minus 9, and I want you to replace all of the x's with negative 17 over 2. And then I want you to evaluate this arithmetic. Okay. Well, the left-hand side, that would be 3 times negative 17. That's negative 51. So negative 51 over 2, and then plus 8. The right-hand side, okay, I want to add these things together. So this is negative 17 halves, and this is negative 9. So I could use the butterfly formula or whatever. Find a common denominator. This would be negative 17 over 2, and then minus, how about 18 over 2? Okay, so then this would be negative 51 over 2 plus 16 over 2. And since these have the same denominator, that'd be what, negative 35 over 2? And this would be what, after you do that one? Also negative 35 over 2. Okay, so we evaluated the equation. So is this an equation?
Yes.
Yes. What does it evaluate to?
True.
True. Okay, good. Any question about this? So, is 14 equal to negative 7 an equation? Yes. And it evaluates false. Is negative 35 over 2 equal negative 35 over 2 an equation? Yes. And it evaluates true. Good. Any question about this? Okay. So now, what I'm sure many of you did is you took that equation that I wrote, and probably before I could finish speaking, you were already starting to perform manipulations on the equation, because that also is what you've been psychologically conditioned to do before you got here, right? You start doing things. So the thing, now we're going to talk about a proposition called truth preservation. So specifically, we're going to talk about the things you can do to an equation which do not modify its truth value. So to be more, to kind of bring it into real life a little bit for a moment, there's some things that you can do to a house, and in the end, it'll still be a house. For example, you could paint the house. At the end, it'll still be a house. You could even paint the house pink. And that might not even be your thing, right? Pink house. But at the end of this operation, it will still be a house. What's something that you could do to a house so that at the end of that operation, it would no longer be a house?
Demolish it.
Yeah, burn it down, right? Wouldn't be a house anymore after that. So now what we're going to talk about is just what can you do to an equation so that if it was true to begin with, it'll be true in the end. And if it was false to begin with, it'll be false in the end. Because these are the things that are permissible. Okay? So the first one is that you could add the same real to both sides. So for example, 5 equal 5. Is that true? It is true. So now I'm going to add the same real to both sides. So plus 2, say, and plus 2. So what would the new left-hand side be? 7. And what would the new right-hand side be? Also 7. So how about, so the equation we began with, is it true? Yes, it evaluates true. The equation we ended with, is it true? Yes. So adding the same thing to both sides preserves the truth. But also importantly, notice, how about 5 equal to 9? Is that an equation? Yes. Is it true? No. Well, we'll add 2 to both sides, so we'll fix it, right? Adding 2 was something that worked good. So what is the new left-hand side? 7. What's the new right-hand side? 11. So notably, I'd like for you to observe that we began with an equation that was false, and then we added the same number to both sides, and we ended with an equation that is false. So by truth preserving, I mean that if you begin with the truth, you end with truth. If you begin with false, you end with false. Okay? 2. Besides adding this same, oh, by the way, because there are negative reals, you could add a negative real number to both sides. But we usually don't say add negative real number to both sides. We usually say subtract the same number from both sides. But that's a language thing. So this covers addition and subtraction. So we could multiply the same non-zero. So important that I wrote it in red. Real to both sides. So for example, how about 5 equal to 5? So is that true? It is. What if we multiply both sides by 3? What is the new left-hand side? 15. And the new right-hand side? 15. Terrific. Multiplying by 3 preserved the truth. We started with 5 is 5, that's true. We ended with 15 is 15, that's true. Okay, also, how about 5 equal to 9? True or false? It's false. Is it an equation? Yes, it just evaluates to false. So let's multiply both sides by 3. The new left-hand side is 15. The new right-hand side is 27. So how about that? True or false? False. So I'd like for you to observe that multiplying both sides by 3 preserves the truth. If it was true in the beginning, it was true in the end. If it was false in the beginning, it's false in the end. So now here's something that's probably been missing from your... this all is probably quite obvious to all of you, and I'm glad for that. But here's something that is perhaps less obvious. How about this equation? 5 equal to 9. Is that true? It's false. Let's multiply both sides by 0. What is the new left-hand side? 0. What is the new right-hand side? The equation that we began with. So is it an equation?
Yes.
Yes. What does it evaluate to?
False.
False. The equation we ended with, what does it evaluate to?
True.
True. You just burned the house down. Okay? Burned it down. So, this is an illegal operation. You cannot multiply both sides of an equation by 0. And for the same reason, because you could multiply by, because any non-zero is also, 1 over that number is also non-zero, you can also divide. So this means multiply or divide, is what this one means. You can multiply both sides of an equation by a non-zero number, and the truth will be preserved. You can divide both sides of an equation by a non-zero number, and the truth will be preserved. But if you multiply both sides by 0, or divide both sides by 0, the truth is not necessarily preserved. And also I'd like to point out that the equation 0 equal to 0 reminds me of an oxygen molecule. Right? From chemistry class? Okay, so now, here's something that every time I log onto social media, I get the following image. Facebook, Twitter, whatever. So here we go. Someone sends me this. So let's start with A is equal to B. Okay, now I'm going to add A to both sides. So A plus A is B plus A. So is it legitimate to add A to both sides? Yeah, because we just got finished saying that's unconditionally truth preserving. So no problems. Okay, so now I'm going to simplify the left-hand side because A plus A, that's just, I can write that shorter as 2A. Okay, now I'm going to subtract, I'm going to subtract 2B from both sides. Terrific. Now I'm going to simplify a little bit. Left-hand side has a common factor. What? 2. So I can factor out that 2, and then I put what in there to make it right? A minus B. Okay, and I'd like to observe that the right-hand side can be simplified a little bit because it can be collected. After collection, what is the new right-hand side? A minus B. And I'm going to go ahead and just parenthesize this so that you can see clearly that, both sides have a common factor. Okay. So now what I'm going to do is I'm going to take that and I'm going to divide both sides by A minus B. Okay. Then now, if you do that and perform the cancellation, what's the new left-hand side? 2. And what's the new right-hand side? 1. Every time I log into Twitter. Okay. So what's not I mean, obviously this can't be right. Okay, because if we start at the beginning with the presumption that A is in fact equal to B, that is in fact true. How about this equation? Is this one true or false? False. So can someone explain to me what happened here? What went wrong? Well, let's number the equations so that we can talk about them intelligently. So this is 1, 2, 3, 4, 5, 6, 7. So we begin with the presumption that 1 is true, that A is in fact equal to B. Yes?
If A is equal to B, then A minus B in step 6 would be 0.
Ah, so let's have a look. Let's look at the steps carefully, one at a time. So from 1 to 2, what did we do? What was the operation? We added A. Is that truth preserving? It is. Adding A to both sides is unconditionally truth preserving. It doesn't matter what A is. From 2 to 3, all that we did is we said that A plus A is 2A. So that's obvious. That preserves the truth. So we subtracted 2B from both sides. Is that truth preserving?
Yeah.
Yes, because 2B is a number and negative 2B is a number. So we added negative 2B to both sides, which is unconditionally truth preserving. Here we perform some algebra simplifying, and then what happened from 5 to 6? So what operation? We divided by A minus B. So is division of both sides unconditionally truth preserving?
If it's a non-zero.
If you're dividing by something that isn't 0, and so as she observed, is A minus B 0? It sure is, because we started with the presumption that A is B. So A minus B is 0. So this step right here, this is illegal. This is division by 0. Okay. So what that means is that equations 1 through 5 have the same truth value. They're all true, every one of them. However, the movement between 5 and 6, the truth value was not preserved because an illegal operation was performed. So these 5 are true, and these 2 are false. Okay, and what our class is going to be about, in large measure, is we're going to be obsessed about equations and trying to find the set of all values that you can plug in so that the equations are true. And we're going to be performing all manner of operations upon those equations to try and figure out the values for which the equation evaluates true. And we're going to have to carefully keep track of, well, I just performed an operation. Was that truth preserving? Or did that potentially modify the truth in some way? And we're going to have to be carefully tracking all of this. Okay, good. So any question about this? Okay. So among the things that we'll have to pay attention to for equations is the following. So for example, here's an equation. 2 over x minus 5 is equal to, say, x plus 1 over x, I don't know, minus 8. So here's an equation. Here's an equation. And I could request of you, I could say, please evaluate at x is 1. So how about it? Well, the left-hand side would be 2 divided by negative 4, right? And the right-hand side would be, what? 2 over negative 7? So is this an equation? Yes. What does it evaluate to? False. Okay. Now, could you plug in just any old thing that you wanted? Like anything at all? I mean, we just plugged in 1. Could you plug in anything? Yeah?
It can't be 5, it can't be 8, and then you get 0 at the bottom.
Right. So consider the left-hand side just by itself. It's an expression. This expression has a natural domain. So the left-hand side itself cannot be evaluated at 5. How about the right-hand side? The right-hand side can be evaluated at 5, but the right-hand side cannot be evaluated at 8, which means that this equation in total cannot be evaluated at either of those points. It cannot be evaluated at 5. It cannot be evaluated at 8. And so the natural domain of an equation is the intersection of the natural domains of its left and right-hand sides. So it's exactly what you think it is. So please tell me, what is the natural domain? What is the natural domain of this equation? So in plain language, what is it? Anything but 5 or 8. And if I asked you to give this to me in interval notation, what would you have to write? Negative infinity
To 5.
to 5.
Union.
Union, yeah.
5 to 8.
5 to 8, okay.
Union 8 to infinity.
Good. Now, I always like to make questions like this have an 8 in them because I think it's funny that 8s and infinities are like sideways versions of each other. So, I'll tell you a common joke, not really a joke, but at any rate, something that happens frequently in a math class, is that your instructor will give you an equation, that you perform a sequence of algebraic operations on it, that you probably are already somewhat familiar with, and then you end with the statement x equal to 7. And so you say, I think 7 is one of the places where the equation evaluates to true. Except it isn't, because it wasn't part of the natural domain in the first place. So this is a very common occurrence, right? So notice that this equation is not evaluable at 5 or 8. And therefore, it is necessarily true that it could not evaluate to true there, either, or false, for that matter. Good. Have a nice Monday.